Hello guys, today I'm gonna show you how to use the method of the integrals for calculating the centroid. But I'm gonna start with a problem that is a little bit more advanced and not just a single problem of calculating any single shape. Let's say that you want to calculate a shape, the centroid of this shape. And this shape is defined by this line and by this parabola. Well, the first thing that we have to do is identify these intersection points, because these intersection points are the ones that are gonna tell us what is the area, how the area is defined. So how do we find those intersection points? Just by making these two equal. So I can say that x has to be equal to 1/4 of x squared. This passes to the other side, or I can simplify this if you want to, which is going to give us the first trivial solution, or the first solution is x equals 0, because if x equals 0, this satisfies. And the other one is just simplifying these two and pass this 4 to the other side, and then x equals 4 will be the other solution for this intersection. Now, if we have this x equals 0 and x equals 4, we can just come back here or here, which is the same basically, and then I can say that for x equals 0, if I plug it in here, y is going to be equal 0, and for x equals 4, then y is going to be equal 4 also. Now that means that we already have this point, and I can establish my system of axis of reference here, and I say this is my x, this is my y. This point is going to be the 0, 0, and this point here is going to be 4, 4, meaning this distance is going to be 4 in x, and this distance is going to be 4 in y. That's the first step that we have to do. And remember, the area is this area now. Okay, the first method is the same method that I went over, or one of the methods that I went over in the classroom. And the first method, if we want to calculate the x position for the center of gravity, remember the x position for the center of gravity is going to be x dA divided by the integral of dA. That's basically what it is. And if I want to calculate in y, well, it's going to be y dA divided by the integral of dA. Let's start by calculating my differential of area. And as I explained, let's say that I want to work with x, the first one, meaning I'm measuring x in this direction, and my differential of area, then I selected perpendicular to that one. This is going to be my differential of area, meaning this is going to be dx, and this is going to be this strip is going to be my differential of area. This differential of area is defined by this line and this line. So if I say this is y1 and this is y2, basically this height for this line is going to be y1 minus 1, 2. And my differential of area is going to be y1 minus y2 multiplied by dx. Now that y1 here is just the equation that we have for y1, so it's x minus, and y2 is this 1/4 of x squared dx. So if I want to calculate the area, I can integrate both of them, and because I'm measuring in x, I'm measuring, and my limits are going to be from 0 to 4. This is 4 also, but remember, we are doing from 0 to 4 in this direction. That means that the integral of differential of area is going to be my area, and the integral of this is going to be x squared divided by 2 minus, this is x cubed divided by 3, but I have another 4 here, so it's going to be 1/12 of x to the third, and this is going to be evaluated between 0 and 4. meaning that my area is going to be 4 squared divided by 2 minus 4 to the third divided by 12, and that is going to give me an area of 1/3 of feet square, because I didn't say that, but the dimensions here were in feet. Or if you don't have this unit here, well, it doesn't matter, unit square. But let's say this is feet and this is feet, because units in feet. Once we have the area, then we can come back here, and I'm going to work with the top part of the integral first. The top part of the integral is x dA. Well, the only thing that I have to do is solve the integral of x multiplied by dA, but dA is this part here, so it's going to be x minus 1/4 of x squared dx from 0 to 4, and this is going to be equal to x times x is x squared. When I do the integration, it's going to be x to the third divided by 3, and this is going to be x to the third. When I do the integration, it's going to be x to the fourth divided by 4, but I have another 4 here, so it's going to be divided by 16, and this is going to be evaluated once again between 0 and 4, which is going to be 4 to the third divided by 3 minus 1/16 of 4 to the fourth. And remember, if I add the area here, because this is the equation, the integral of the A, but the integral of the A is the area, so I'm going to divide this by the area, and my area is 1/3, meaning the position or the location for the centroid is going to be in x, is going to be 2, and if we say that our units are going to be in feet, then this is going to be 2 feet. Done. This distance here for this location is going to be 2. First part completed. Now the second part would be y bar. Y bar. Meaning, by using the same drawing here, I can measure y. No, I'm gonna draw it again. So I'm gonna have this area here. This is 4. This is 4. And remember, in feet all the time. So now I'm going to measure y in this direction, and my differential of area has to be in this direction if I use that approach. This is y and this is dy. Yes, dy. And this is my differential of area here. But now remember, this equation was y equal x, and this equation was y equal 1/4 x squared. Now my differential of area in this occasion is defined by this x minus this x, because it's delimited by the parabola minus the straight line. So I have to solve for x. In this case, x equal y. That's going to be called x. I call it last time y1, x1 in this case should be, or y and x. So this is going to be y, x1 is going to be y. And this one here, if I solve for x, x is going to be square root of 4x or 2y, or I can say 4y square root of that, or I can say that x equals 2y to 1/2, and of course I'm going to say that this is going to be x2 now. So my differential of area is going to be this x2 minus this x1, which I'm just going to call x because it's the same, x1, no, x2 minus x1 dy, x2 minus x1 dy, but x2 is this value, so my differential of area is going to be 2 times y to the 1/2 minus x1, which is y, and everything is going to be multiplied by dy. That's my differential of area. If I apply the equation, remember y bar is the integral of y dA divided by the integral of dA, which I already had this integral I calculated before, and it's 8/3. I don't have to calculate it again, but I have to calculate y divided by dA. So this is going to be the integral of y multiplied by dA is this here. And it's from 0 to 4 because I'm measuring in the direction of y. Be careful because this is also 4, but remember when we measure in this direction, we are evaluating y, we have to be evaluating in the y direction. So this is going to be divided by the area, and this is going to be, this is 1/2 plus 1 is 3/2 plus 1 is 5/2. So basically this is going to be 2 times y to the 3/2 plus 1 is 5/2 divided by 5/2 minus, this is y times y is y squared. When I do the integration, it's going to be y to the third divided by 3, and this is evaluated between 0 and 4 and divided by the area, which at the same time, remember, area is 8/3. 8/3 we calculated before. So then this is going to be 2 times 4 to the 5/2 minus 4 to the third divided by 3. This is divided by 5/2, and everything is divided by 3. I can pass this here if I want to and say this is 4/5, or you solve it in any way that you see fit, and then your y bar is going to be equal 1.6, and because we say the units that we're using are fit, this is going to be fit. This is the first way that we have for solving this problem. Now, there's another way that I also explained to you guys before, but I want to show it to you again in this example. Now, the first part is the same part. When I calculate my x, this is going to be my x exactly as we proceed at the beginning of the problem. Now, instead of switching my differential of area, I can keep the same differential of area that I had before and use that differential of area. Let me do the drawing again so it's easier to follow. I have this and this and this and this, and we selected before this differential of area here, and this is our differential of area, and we say that this is x in this case. That was what we did before, and remember always this distance is 4, and this distance was 4 also here to the edge of that 4. But now we have to measure in y, because what we want to calculate, or I'm going to calculate the x in the same way, but when I calculate y, I say it's the integral of y dA divided by the integral of dA, which is the area, and I know what the area is. So I want to use this approach now, and I said, and using the same differential of area. Now, if you remember, this is a strip because this is a differential. This distance here we say is the x, so it's really small. It's the same thing if I ask you, okay, let's imagine these are your axes of reference here. This is x and this is y, and I tell you this is a wire here in this direction. Where is located the center of that? Well, the center of that is located in direction x bar. Perfect, because that's a wire. Now, in this direction, if this is L, let's say, where is located the center of that wire in this direction? Obviously, it's going to be at the center of this distance. It has to be at the center, right there. What happened in our case is that we said that this distance, it was before called y this minus y that, and we call that distance y1 minus y2, meaning x minus 1/4 of x squared dx. That was our differential of area, the same differential of area that we had before. The distance of that differential of area will come from the centroid of that shape to my axis. That's going to be the distance that I have to measure. So my whole problem is how to find this distance. Well, it's not that difficult because we know this. And we know this is going to be half of the distance. So first, this distance here, from here to here, is no other thing that, remember we call this equation y2 equal 1/4 of x squared, and this equation is y1 equal x. That's what we did before. So this distance is y2 minus y1. That's the total distance. But I'm looking for half of that distance, so it's going to be divided by 2. That's true, this is the centroid of this wire, but that's referred to this point, and I have to refer it to my x-axis here. So I have to add this distance, and this distance, we call it y2. That's the value that I have to put here. That's exactly the value that I had to put there. So if I do that, then this distance or this value, remember, is going to be y2 minus y1. So y2 is this. It's going to be half of this minus half of this, or no, this minus this in this case, because this is bigger. So y1 minus y2. So this is going to be x 1/2 because of this half, minus 1/2 of y2, and y2 is this here. So it's going to be 1/2 of 1/4 of x squared. I already covered this part, plus y2, and y2 is this distance, 1/4 of x squared. And then we solve this part. When we solve this part, I have 1/8 negative 1/4. This is going to be 1/2 x plus 1/8 x squared. There you go. That's the distance that I'm looking for. Once I have this, we have the differential of area that we calculated before, and then our y bar is equal to the integral from 0 to 4 of this value, but this value is not y anymore. It's this. Is 1/2 x 1/2 x plus 1/8 x squared, and that's multiplied by my differential of area. Remember, the differential of area that we calculated before was this here. So multiply by x minus 1/4 here. X minus 1/4 x squared dx. And everything is going to be divided by the area. You can foil this, and when you foil this, then you're going to have 1/2 x times x. So that means that it's going to be 1/2 x squared. This times this is going to be negative 1/8 x to the third. This times this is going to be positive 1/8 x to the third. And this times this is going to be negative 132 x to the 4. This and this cancel out. Everything is multiplied by dx, and everything is divided by area. And then when we solve this integral, this is going to be 1, this is x to the third divided by 3, but I have a 2 here, so 1/6 x to the third, and this is going to be 32. This is 5 when I integrate it, so this is going to be 160 x to the fifth divided by my area, that if you remember is 1/3, and this is going to be evaluated between 0 and 4. And when you plug this here, then you have 1/6 of 4 to the third minus 1 divided by 1/64 to the fifth divided by 8/3. And this is your y bar. And that y bar is going to be equal to 1.6 in the same way that we calculated before. Why use this if it looks more complicated than just using the other approach, which was this one? Because not all the time you can use this, or sometimes it's really difficult. For example, what if you have a shape now, and the shape that you have is something like this? And I want to calculate my differential of area. Let's say when I go for x is equal to the integral of x dA divided by a. Perfect, no problem. I measure x, I calculate my dy, my d area, I'm sorry, in this direction. This is x, this is my d area, this is dx. And this distance is going to be the equation of this line, which could be whatever equation is. But you know how to do it. No problem. Now, when I go in the other direction, if I say, okay, and I'm going to say y bar equal the integral of y dA divided by the area. Or, you know, when I do this, I'm referring to this, but it's like I already calculated. So, if I do the other method, when I go here, there's no, look at what happened if I go here. Let's say this is going to be y, and my differential of area is going to be this one. And that is wrong, because that differential of area is not that. It's this part and this part. But this part is not included. So what do we do? Well, instead of using or changing my differential of area, I use the same differential of area here. And I say that y bar is y. But it's not going to be y now. Remember, this y represents the distance between the axis and the centroid. And the centroid is here. So if this equation is y equal blah, 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 blah here, whatever parabola or cubic equation or shape you have here, if this is the y, this is not the same that I'm referring here as y. What I'm referring in the second method is to this distance, and this distance is going to be half of that. That's why you see some books that they say y half times dA divided by the area. This is not a constant. This is not always like that. It's just the distance from the axis to the centroid. And then I can use the same differential of area that I used before. And no problem with that. This type of situation, I'm not going to say that it's impossible to solve using a differential of area in this direction, but it's much more complicated using like that. So in that case, you should be using the same differential of area that you used before. Now, I'm going to solve the same problem again. Yes, same problem again. And I'm just going to do it in this way because some people ask me if they can use double integrals. And yes, you can use double integrals. So just use the method of double integrals for solving that example. If I'm going to use double integrals, remember the equation is going to be x bar is going to be the double integral of x dA divided by the double integral of dA, because now my dA is going to be this, dx dy, so I need a double integral for that. And my y bar is going to be also the double integral of y dA divided by the double integral of dA. Now going back to the same example again, I have this, x, y, and I'm using this example because it's not the most straightforward example. That's why I'm doing it. Remember, this one here is y equal x, and this one here is y equal 1/4 x squared. Distance here 4 we calculated, distance here 4 we calculated before. Now my differential of area is gonna be this. It's not a strip anymore. Now it's just a plain and simple differential in both directions. My differential of area is gonna be dx dy. Okay, this type of problems, the first thing that we have to do is describe the area. The area meaning this area, the area that I have to calculate. Okay, in the x direction. In the x direction, my area is defined. Let's say that I'm gonna draw a line in this direction. If I'm gonna do that and I'm gonna draw a line in this direction and I have to define that area, I will say that that area goes from this point to this point. So what is this point? Well, this point here is x equal y, this point, and this point here is defined by x equal 2 times y to the 1/2. Just solving for y. So in the x direction, I know that this point here, which is y, or which is x. Give me a second because I have to tell the people to lower the voice. Okay, so in the x direction, my area is going to be defined by this and by this. So I know this value of y has to be smaller or equal than x, but the x at the same time has to be smaller or equal than 2y to the 1/2. And once I have that, I basically define this line. And that line, now I'm going to move it in the y direction from here to here, or from here to here. So in the y direction, if I have to define in the y direction, my y is changing from 0 to 4. So 0 is smaller or equal to y, and smaller or equal to 4. That's what defines my area. So working with this problem again, the first step, let's find the area. So I get rid of this denominator, and let's calculate the area first. It's page 3. So if I calculate the area, my area is going to be the double integral of dA. And remember, y is going to be smaller or equal of x, and smaller or equal than 2y to 1/2, and 0 smaller or equal than y, smaller or equal than 4. So those are my inside limits. And these are my outside limits. So when I do that, my area is going to be the double integral of dx dy, or it's going to be the 0 to 4 and y to 2y and 1/2 of dx dy. The way you solve this, you know this better than I do actually, because you first solve this integral. And when you solve that integral, basically you keep the outside integral the same, and then the integral of dx is x. So this is going to be basically x, and it's going to be evaluated between y and 2y to the 1/2 times dy. When you solve this, then you are going to have the integral of from 0 to 4 of this minus this times dy, or this is going to be, if you solve this is going to be 1/2 plus 1 is 3/2, so 2 times y to the 3/2 divided by 3/2 minus y squared divided by 2 from 0 to 4, and when you evaluate that, that's 1/3, which is the value for area that we had before using double integrals. Now let's work with the top part of the integral. The top part of the integral is the double integral of x dA. which is the integral from 0 to 4 of the integral from y to 2y to 1/2 of x dx dy. Because remember, x the area is the x dy. And this is what I'm going to be solving first. So when you solve this is going to be the integral from 0 to 4 of x squared divided by 2 dy. And this is evaluated between y and 2y and 1/2. And this is equal to, evaluating this is going to be 2y and 1/2 squared, because I'm substituting it here, divided by 2 minus, now with this limit, y squared divided by 2. This is the evaluation of this part. And this is square 4 divided by 2 is 2 and 1, 2y minus y squared divided by 2. This is the evaluation of this part. So going back to the integral and plugging this there, this is going to be the integral from 0 to 4 of this. dy, which is 2y squared divided by 2, basically is y squared minus y to the third divided by 6, between 0 and 4, and this is 4 squared minus 4 to the third divided by 6. This is 16 third. And remember, this is the top part of the integral, so our x bar is going to be 16 thirds divided by the area that we calculated before, which is 8 thirds. Remember, this is the top part, so this represents the integral, double integral of x dA, and this represents the double integral of dA. And when you divide this is equal to 2, and our units, we say that they were feet, so x bar equal to feet. That's the same value that we got before. Do I like this method? Not really, not particularly, no. But at least you know that yes, you can do it, and that can work for any type of situations also. But you have to really be good at math, and you really have to like that part of doing it like that. So I enjoy doing that one problem, if I have time, just for the sake of knowledge. But if I can use the other method, you can betcha I'm going to use the other method. Now if we have to calculate the other coordinate, y bar is going to be the double integral of y dA divided by the area. In this case, I already know. I'm not going to go again over this. But then you have to do the same thing. The integral from 0 to 4 of the integral from y to 2y to 1/2 of y dx multiplied by dy. Because remember, dA is dx dy. And now we solve this. So if we solve that, it's going to be the integral. Let's solve let's solve first this part, the integral of y to 2y and 1/2 of y dx. If I had to solve this first, then remember the differential is dx. So when I do that, this is going to be the integral from y to 2y and 1/2 of y. It's going to be y times x, because this is already here, and this is going to be the parameters that I have to evaluate that from y to 2y and 1/2, and this is going to be equal to y that multiplies 2y and 1/2 minus y. So this is going to be equal to 2 times y to the 3/2 minus y squared. This is the inner part, this part of the integral. So I'm going to plug this back into there, and this is going to be 0 to 4 of this. dy. And now this is going to be equal to 2 times y to the 5/2 divided by 5/2 minus y to the third divided by 3 between 0 and 4. So that's 2 times 4 to the 5/2 divided by 5/2 minus 4 to the third divided by 3, and this value is 6415. And remember, my y bar is going to be the double integral of y dA divided by the double integral of dA. This part is this one, 6415, and the area we calculated before, and it was 1/3. When you do this division, then we get that y bar is equal to 1.6 feet, which is the same result that we got before. Once again, do I like this method? Not particularly. I can enjoy it as a curiosity, but if I have to do an exam, I wouldn't do that. I would use the easiest method is always use x perpendicular, y perpendicular, selecting the differential of area perpendicular in strips perpendicular to the distance that you are measuring, or selecting the differential of area in the way that I showed you before. So you can also remember, if you are using, let's say now you are doing, let's say that you want to calculate the differential of area of a square like we did before, or a rectangle. This is B and this is H. Well, if I'm measuring x, I can do two things. I can measure x and say this is my differential of area, and my differential of area is going to be what? This is dx, and this is h, so it's going to be h dx. And I can say that my x bar is going to be the integral of x dA, so it's going to be x times dA, but dA is h dx from 0 to b divided by the area. This is what we did before, but if I want to use the same differential of area for measuring y, then what I have to do is just this. This is my differential of area. Is what? Differential of area is h dx, same one. But the centroid of this strip, once again, is here. So this distance is h divided by 2. And remember, this is b and this is h. So if I want to calculate my y bar, then it's going to be the integral from whatever to whatever, from 0 to h, no, from 0 to b, of h divided by 2 multiplied by h dx. When you solve this is going to be h squared b divided by 2 divided by the area, remember, and the area is bh, so this h and this h cancel out, and this is going to be h divided by 2. In this case, I didn't finish it, but it's the same. H times b squared divided by 2 divided by bh. This and this cancel out, and this is b divided by 2. You can use it, or instead of using this, you can go back to the method that we explained before. Then you say, oh, I'm going to measure y, but this is going to be my differential then. And my differential, if this is dy and this is b, my differential of area, I change it. I don't use that anymore. And it's going to be b times dy, and then I use the integral for calculating the y bar. I use the integral of y multiplied by my dh, which is b dy, from 0 to h, divided by the area, and that's equal to by squared divided by 2 divided by the area, evaluated from 0 to h, which is also bh squared divided by 2 divided by bh, cancel, h divided by 2. Either you use this or you use this. Two methods. And this is just for the very simple example, but I want you to go back to the original one that I saw and dissect it, go in detail, try to check it. I'm not gonna ever gonna ask you something as difficult as that in a test, but work it out. Try to solve it, and now you know that you have 3 different ways, at least that I explained, that you can use for calculating and solving examples for centroid using the method of the areas. I hope that you enjoy this video also, and then I'll see you in class. Have a good day.